of the weekend on the beach. And bye bye.
Ciao, grazie. Cominciato. Ciao, grazie. È stato veramente grandioso, veramente. Senza di te qui sarebbe andato tutto a roda. Allora tu mi dai questa chiave, ci vediamo. Sì, importante adesso.
We will introduce the idea of pseudopotentials, and we will do an exercise to build a real pseudopotential using the Pt1.x atomic code. So in this introduction, I will try to give you which is the theory behind the construction of the pseudopotential, and in the laboratory we will see how, in practice, we construct this pseudopotential. We will take silicon, that is a simple element, as our goal. So we want to generate a pseudopotential of silicon. So this is an outline of the talk. I will start by introducing the all-electron radial equation, that is the equation that is solved by this atomic code. Then we will introduce the concept of non-conserving pseudopotential. In particular, we will see the use of the concept of logarithmic derivative, and we will try to discuss why this concept is important and why it is used so often in the pseudopotential construction. Then we will discuss the steps that are needed to generate a pseudopotential. We will discuss how this pseudopotential generated in the atom has to be modified, or has to be what we have to do to pass from the pseudopotential generated in the atom and to the pseudopotential that we use in the solid. And then we will discuss some transferability tests that can be done in the atom. As a third part, we will discuss the concept of fully separable pseudopotential, the so-called Klein-Bylander pseudopotential, and we will see why these pseudopotential are much more convenient from a numerical point of view, so that basically all the pseudopotential nowadays are fully separable. So let's start from the beginning, from the Kohn-Sham equation, that in atomic unit in general is written like this. There is an external potential that is screened by the Hartree and the exchange and correlation potential. So we have to solve this kind of equation and to apply it to the system of interest. In particular, we want to apply this problem to an atom. So this external potential that acts on the electron gas is the potential of the nucleus. And for an atom, we can write it like this, minus Z, in atomic unit, this is Q squared, that is the electron charge is equal to 1. So Z minus Z divided by R, where Z is the nuclear charge, okay, Q is the electron charge. And then this potential, as you can see, depends just on the distance of the electron from the nucleus. So it is spherically symmetric. At least the external potential is spherically symmetric. If we assume that this external potential will produce a spherically symmetric charge density, so that the charge density that we obtain by taking the square modulus of this wave function is also spherically symmetric, and we will see which hypothesis one has to do to have a spherically symmetric charge density. Then one can see that also the Hartree potential, the exchange and correlation potential, at least in the local density approximation or in some local approximation, are functions that depends on the modulus of R. And in this case, all the external potential, all the Kohn-Sham potential, we call all these the Kohn-Sham potential that acts in this problem is spherically symmetric. And we can exploit this spherical symmetry to write the solution of this problem in this form. So the product of the function of the radial variable alone and a spherical harmonics. So one has to introduce 3 quantum number. N is the main quantum number, L is the orbital angular momentum, and M one of its projection along a quantization axis. So in general, N, which is the main quantum number, is a positive integer. It is 1, 2, 3, and so on. And L goes from 0 to n minus 1. L, the orbital angular momentum, goes from 0 to n minus 1. M goes from minus L to L. And Y and M are the spherical harmonics that, as you know, are the eigenstate of the square of the orbital angular momentum and of one of its components. Okay. So if we insert the solution dividing by R, so pay attention that from now on our radial, the real radial part of the wave function is the wave function that we study divided by R. So for this wave function, we obtain a differential equation, an ordinary differential equation that can be written like this. There is a second derivative with respect to R, a centripetal potential, L plus 1 divided to R. So this potential depends on the orbital angular momentum. And then the Cone-Sham potential, that is a spherically symmetric radial function. The radial function depends on n and L, so on the principal quantum number and on the orbital angular momentum number. And okay, we define the Cone-Sham potential as so to determine the charge density, we have to know how many electrons we have. So what is the one important input of this problem is the atomic charge. Not only the atomic charge Z, but also how many electrons there are. It may happen that the number of electrons is equal to the charge of the nucleus, then we have a neutral atom, or we have less electron than the charge of the nucleus, and we have a positive ion. A positive ion. If we put more electron than the charge of the nucleus, there are possibility that the calculation does not converge. So, knowing the electrons is one thing. The other information that we need to specify completely our problem is how do we occupy the atomic level. We can decide to use the usual Fermi occupations and then to distribute the electron among the lowest energy state, or we can try to decide to study an excited configuration where we put electrons also in states that are not the lowest energy states. This, however, is determined by the configuration of the atom that is given by this occupation number F and L. So for each N and L, the maximum number of electrons we can put, so usually the L is also indicated by some letters. So L equals 0 corresponds to S state, L equals 1 to P state, L equals 2 to D state, and so on. And the maximum number of electrons that we can put is 2L plus 1. So 2 for the S state, 6 for the P state, 10 for the D state, and so on. Note that we have not an occupation of that depends on the projection M, the projection of the orbital angular momentum along a quantization axis, because if we occupy in a different way different value of M, we would obtain a non-spherically symmetric atom. So the hypothesis that one has to do here is that if you have a shell that is not completely filled, you have to distribute uniformly among the available M the electron that you have. And so you can only specify the occupation of N of the N and L shell, and all the M are occupied, dividing the number of electrons by the number of places in that for that N and L. Okay, the charge density then is given by taking the square modulus. So if we take the square modulus of the solution of the differential equation with adding them the square modulus with the occupation that we have introduced, we obtain 4 pi r square the charge density. So we will work in the atom with this charge density rho tilde that has the property that if you integrate in the radial variable from 0 to infinity, this will give the number of electrons. So how do we solve the radial equation? Okay, we use in general for Schrödinger-like equation, so that in the non-relativistic case, we use the Numerov method, discretizing the coordinate r by a logarithmic radial grid from r minimum from a minimum to a maximum r. The grid is this one. Is 1 divided the nuclear charge, e to the this x min. You see that, and then e to the I minus 1 dx. So there is practically a linear mesh that goes from x min to x maximum linearly, and then we have the exponential of this linear mesh. This x min that corresponds, so when I is equal to 1, the first point of the mesh is 1 divided by z e to the x min. So this x min that is usually of the order -7, -8, is the first point, the point closest to the nucleus. The x is the spacing of this uniform mesh. So if you want to increase the number of points and the precision of the calculation, you have either to make this x min is a negative number, so either you make this x min more negative, and this means that you put your mesh closer to the origin, or you decrease the x, and this means that you put more point, a finer mesh or point in the linear grid that then is exponential. So the fact to use a logarithmic grid like this one is due to the fact that we need more resolution close to the nucleus, and then we can use less and less resolution as we go farther away from the nucleus. Okay. From input, you can define the value of x min and delta x, and also of r max, the maximum r. But usually the default are quite well tested, and we will not change this value. However, if you have doubt that your result could not be converged with respect to the mesh, these are the 3 parameters that are in the input and that you can control. So the output of the calculation are the eigenvalue of this equation. Notice that this equation is again a self-consistent problem. So you have to solve this equation and find the approximate value for the wave function. Then you calculate the charge density, you can recalculate the exchange and correlation potential and the Hartley potential, and so you repeat the calculation until you have self-consistency, so as in the usual DA problem, so as in the PW. It makes this self-consistent calculation, and after the self-consistent calculation, you find as output the eigenvalue epsilon and L of the radial orbital, the function phi and L of the radial orbital, the charge density, and the total energy of the system. For instance, if we try to run this program called silicon that has a nuclear with 14 electrons, and the electron configuration that we take as the ground state, so we occupy all the lowest energies, so we put 2 electrons in the 1s level, 2 electrons in the 2s, 6 electrons in the 2p, and 2 electrons in the 3s and in the 3p state. Yes.
Why the radial grid are decreased exponentially?
Because the solution of this problem have variation on a finer scale close to the nucleus, and there you need a lot of points. But then to keep that fine mesh everywhere would create a quite big mesh, and so it is convenient to, as you go far from the nucleus, to decrease the distance between, to increase the distance between points. Okay, so what are the results that one obtained by doing the silicon atom with this? Here is an example of the result. As you can see, there is the 1s state, the 2s state, and the 3s state that can be distinguished because they are the solution of the equation with L equals 0. And as we increase n, so from the 1s to the 2s, we have one more node. So the 1s has no node, the 2s has one node, and the 3s has 2 nodes. The 2p functions that are solved, that are found solving a different equation, an equation in which we put here L equal 1. So for each L, we solve a different equation and find a set of a value of n. So here, the 2p level has no node, and the 3p has one node. So I'd like you to look at the eigenvalue of this problem. These are given here in Rydberg. The 1s is at minus 130 Rydberg. The 2s is at minus 10, and the 2p at minus 7. Instead, the 3s and 3p are minus 0.7 and minus 0.3 Rydberg. And so you see that there is a clear distinction in energy, at least, between the 3s and 3p states that are that have not very large energy, binding energy, and the other 3 states that are quite deep inside the atom. If we look at the spatial of where the wave function have the maximum density, you can see that the 3s and 3p states are mainly localized outside this, let's say, this line. The 2p are sorry, the 3 level are localized outside this line. The 2 level, the level 2p and 2s are mainly inside this range, and the 2s is quite localized close to the nucleus, mainly in this range. So you see that there is a clear spatial separation between the 3s and 3p states and the other states. And this spatial separation allows to define this spatial separation and the big difference between the eigenvalue tell us that when this atom forms a bond, it is probable that there are the big changes of the 3s and 3p electrons, while the levels that are more close to the nucleus tend not to be strongly perturbed by the formation of the bond. And therefore, one can hope to describe the the problem by dealing only with the 3s and 3p. So to describe the behavior of a solid in which there is a silicon atom by using only the valence electrons. But we have to, you see that we have to find a way to describe correctly the behavior of these 3s and 3p electrons, keeping into account that there is in this region, in addition to the nucleus, also the potential due to these electrons. Why we want to do this and not to deal in the problem with all electrons? Probably this has been already explained, basically because we wanted to use a plane wave. Well, first of all, because it is possible. It is something that works, and it is possible to do in a quite accurate way, and in a way that whose accuracy can be systematically improved. But then we want to do it because we want to use a plane wave. So plane wave are not very suited to describe these quite localized electrons, because you would, if you decide to use the plane wave that are necessary to describe the resolution of this 1s state, so the spatial resolution of this 1s state, then you have to use this same resolution everywhere. And in a big, the cell with respect to this distance is quite large. So the number of plane waves that you would require if you wanted to describe with plane wave the 1s state would be huge. And, yeah.
Could you explain more the right side?
This? What it is?
That's the plane wave color.
No, this is not the plane wave. These are the eigenvalue of the atom. And the fact that, and from this eigenvalue, you see that these are minus 130, minus 10, and minus 7. These are quite low in energy. 7 Rydberg in electron volt is 13 multiplied by 7 is quite low, quite deep. So this state can be considered as core state. This division of valence and core states is not always so clean. Sometimes you have to decide if some level are really in the core or in the valence. And there are also practical consideration that tells you if you have to keep the state in the valence or to put it into the core. Here there is a clear division, and so you can think that silicon with 1s and 2p, 1s, 2s and 2p in the core still represent quite well the silicon atom in this region. However, we have to see how this has to be done in an appropriate way.
I have just a curious question at this stage. Is it because of this clean distinction between the deeper level and the valence state, silicon is the next abundant and so stable in nature, 32%? Because if you look at oxygen, about 52.23%, then is the silicon. And silicon, we know everywhere, most stable, most abundant.
Yeah.
Is it because of so?
Now you are making a chemistry question.
It's a fair nuclear physics question.
I don't know the answer really.
It has nothing to do with, of course, chemistry.
Yeah.
But it's a general question that why silicon is so abundant in nature and so stable.
Okay. I don't know the answer.
What did to shift to? What did you to shift on the right side?
Here, what are these numbers?
Yeah.
Well, this is the level 1s, 2s, 2p. Yeah. This 1, 1, 1 is the spin. So since here we are not doing a spin polarized calculation, this is all 1. And this is the occupation. The occupation.
Physics question.
Okay, so we decide in this way. We decide by looking. We have the information of one. What are the typical which are the core states and which are the valence state. But then the second information that we have is what is the typical localization of the valence state. So we start having an idea of where can we start to pseudize this atom. So where it is important that the properties remain the one of the silicon, and where we can change something. You see that even if we would decide to keep frozen this core state, but we would like to keep them in the calculation, then the valence state would be orthogonal to this core state, and this orthogonality makes also the valence state varying on the same scale of the varying on the same scale of the core state. So, in order to use this pseudopotential in the solid, we have in some way to remove this wiggle close to the nucleus.
How much do the small overlap between the 2s and the 2p states with the orbitals that you're going with, the valence orbitals that you're keeping? There's that very small overlap.
Yeah, that's an interesting question, and I think that by the end of the exercise we will answer to this question. However, let's see what are the. Unfortunately, here I have not the time. I would need an entire lecture to tell you what have been the consideration that led to the criteria for constructing a pseudopotential. So many years have passed before people understood what were the critical ingredient to make a pseudopotential that actually works. And so I will give you the final recipe. The reason why these things are important, maybe we can try to understand, but not demonstrate completely. So let's define a pseudopotential. What is a pseudopotential? A pseudopotential is a function that here we write as S and L. It is important that this function for the modern pseudopotential can be different from different L. So we could construct a different, so we wanted to have the freedom to have a different pseudopotential for each orbital angular momentum. And the pseudopotential is a function that you put in an equation like this, and this function must satisfy the following problem. Must have the following property. We want that the ground state solution of this equation, this phi L, that has an index L, because n is just L plus 1. We want the ground state of this, for each L, there will be a ground state solution, the lowest energy solution. Okay, once we have decided for each L, in the previous all-electron calculation, for instance, we have decided that for the S channel, our valence is the 3s. And for the P channel, our valence state is the 3p. Once we have decided this, we want a pseudopotential, this function VPS of L, that has the following property, that the ground state of this pseudopotential coincide, so this function phi L of R must coincide with the corresponding valence state of the same L in the all-electron calculation outside a certain core radius. So we could decide that for each L we take a given radius here, a given point here, a radius, and outside this core radius we want that our pseudopotential reproduce exactly the corresponding valence state. So the 3s for the S pseudopotential, the 3p for the P pseudopotential. So from the all electron calculation, we need to give as input this 3s and 3p state outside a given radius that we choose, and that will characterize the pseudopotential. So this radius for each L are the ingredients that we want to find to generate the pseudopotential. Then we want that the eigenvalue epsilon L coincide exactly with the all-electron eigenvalue of the corresponding all-electron atom. So this epsilon L is the same. For L equals 0 it is the 3s in our case. For L equal 1 is the 3p. So these are two important properties of our pseudopotential. And then there is another. There is another that is critical to have a pseudopotential that actually works. So if there are a lot of functions VPS of L that satisfy these two criteria, but not all of them who give a working pseudopotential. There is another condition that is critical. And let's see how let's discuss a little bit. Before looking at this property, let's note one thing, that if we take a radius here larger than all the core radius that we have chosen for the valence state, well, for r larger than this radius, all the pseudo wave function coincide with the corresponding all-electron wave function. So the potential, the pseudopotential for each L, outside this radius must tend to the pseudopotential of the all-electron equation, because in that region the solutions of this problem are equal to the solution of the all-electron problem, and the eigenvalue are the same. So in this region, all the VPS of L must coincide, and we can exploit this fact to introduce an effective potential that coincides with this Cone-Sham potential outside a certain radius that we call R log. In practice, we can take this R log also smaller the sum of the core radius. However, and then it will be for each L we have a difference. So the pseudopotential is written in this form as a sum of an effective potential radial that do not depend on L. This has only the property to coincide with the all electron 1 outside a local radius. So this is another important parameter in our problem, the local radius. So we have introduced so far the parameters, the radii, the core radii, where the pseudo wave function coincides with the all electron wave function, and the local radius, that is the radius after which the Cone-Sham potential, the effective potential, coincides with the Cone-Sham potential. In this way, this delta VPS of L, you see, is a function that depends on L, and that goes to 0 for an R that is larger either of the R log or of the core radius at that L, depending on which one is larger. And so this is a function that goes to 0 for large R, and all the asymptotic tail of the pseudopotential for all L is the same, and is given by this effective potential. Then suppose that if we do this separation, now we have an additional degree of freedom. We have to decide what is the effective for R smaller than R log. So this is not a unique choice. It will depend on our recipe for the pseudopotential to decide what we do for the effective potential before the local radius. Then suppose that so this pseudo wave function by our definition coincides with the all electron 1 outside the core radius, And so the other freedom that we had is to decide what we do with the pseudo wave function before this core radius. If we had a recipe to obtain the pseudo wave function before the local radius, and we had to decide what is the effective potential, then to find the delta VPS of L is trivial in some sense. This is equal to, if we just notice that we want also that our pseudo wave function has no node, because it is the ground state of our problem. So this wave function has no node, and so the product delta VPS of R multiplied by phi, this object, is equal to epsilon minus all these things multiplied by L. And then, okay, so here we have the eigenvalue minus all the terms that are in the equation multiplied by phi L. And then if we divide everything by phi L of R, that as I just said has no node, so we can divide by something that is never zero, we obtain our form for delta VPS of L. So the construction of the pseudopotential in principle is done when we have decided what is the effective potential and what we do for the pseudo wave function before the core radius at the given end. These are the two information that we have to give to the code, or that the code has to decide. So in order to construct this phi L of R, we have some guideline. And actually the different recipes for constructing a pseudopotential reduced to this point on how they define the pseudo wave function for R smaller than the core radius RCL. All these recipes follow a few guidelines and one important condition. This condition is quite a requirement to construct a pseudopotential that works. Well, some obvious or reasonably obvious condition is that the function phi L that you construct is continuous. So it is continuous, and it has also a certain number of derivatives at the matching point that are continuous. So at the matching point, we have a continuity of the wave function and of at least two or more derivatives. Then it is also useful to construct a function whose Fourier transform decays as rapidly as possible in Fourier space, in such a way that in order to describe at least the atom, you would need a small number.
I ask.
Yeah, we want at least to be able to describe this function in the atom with the smaller possible number of plane waves. So it is also important that we have a pseudo wave function that decays rapidly in Fourier space. However, so if you don't follow this constraint, you will have a pseudopotential that is called a hard pseudopotential, because for describing the same element, it requires a lot of plane wave, more than the minimum that one would like to have. But then there is this strict and important constraint, that is the constraint of norm conservation. Actually, when people understood that, and this is a paper of the 80s of Hamann and others, when they understood that this condition was quite important, the pseudopotential concept made a jump from just a tool to have an approximate description of the materials to basically a tool that is always used. And so norm-conservation, what does this mean? It means simply that we want that the integral from 0 to RC of our pseudo-wave function square modulus is equal to the same integral of the all-electron wave function. So in the previously when this condition, the importance of this condition was not recognized, people constructed pseudopotential taking as a pseudo-wave function exactly something that was equal to the all electron outside the core radius, and then something else inside. But if inside the norm is not conserved, when you renormalize the pseudo-wave function, you obtain that outside the core radius, the two are only the pseudo and the all electron are only proportional, and this wastes the possibilities of the pseudopotential to be transferred into other configurations. Now we will define better this concept. So, how can we start looking if our pseudopotential that we constructed is working or not? Well, the first thing that we can say, so we have used, let's say, this recipe to construct the pseudopotential. Maybe that we have also imposed our non-conservation condition, and then we have imposed these few conditions. So what can we check, first of all, to see that the pseudopotential works? Well, let's consider this problem. Let's take the equation for instance, this all-electron equation, and let's call TL the kinetic energy, this first part. And we can, so you know that the eigenvalue of this equation corresponds to solution of this equation that goes to 0 both in the origin and at infinity. If instead, and these two conditions gives just a discrete set of values that are the eigenvalue and determine the wave function. Suppose that we choose an arbitrary energy. If we choose an arbitrary energy, we can solve this equation at that arbitrary energy, and if we can now impose only the condition at the origin, so we can only impose that the wave function at the origin goes to 0. What happens at large R? Usually this kind of solution will diverge. But then we can find, in any case, for each energy epsilon, a solution of this all-electron problem, and we will have a function C of epsilon, a radial function. Now we can ask, okay, we constructed our pseudopotential fitting the eigenvalue with the recipe that we have seen before. What if we use this pseudopotential at an arbitrary energy epsilon? So does the solution phi epsilon here will reproduce my all-electron equation or not? And how well? Well, it is clear that if the energy is exactly the eigenvalue, by construction, the pseudopotential has to reproduce the all-electron solution. But as you move a little bit from the eigenvalue, if the pseudopotential is good, you still reproduce the all-electron equation outside a certain radius. That's clear. But even outside this radius, if the pseudopotential is not good, your pseudo wave function will not reproduce the all-electron wave function as soon as you move from the energy that has been used to fit the pseudopotential. So it is important to have a pseudopotential that is able to reproduce for a certain range of energies the all-electron solution. And in order to quantify this ability of the pseudopotential, it is useful to introduce the concept of logarithmic derivative. So we take a given radius r, and we calculate this r that is usually slightly larger or close at least to all the core radius, slightly larger than all the core radius. We can calculate the derivative with respect of r of the logarithm of this function. So this would be 1 divided the function multiplied by the first derivative of the function at that point. This, in general, is a function of the energy that we have taken to define the solution. It does not depend on the normalization that we have chosen for our function, because it is a ratio of two functions. Or if you put a value here in front, multiplied by a, the logarithm is equal to the sum of the logarithm, so the derivative is not dependent of a given factor on the wave function. Well, if the logarithmic derivative calculated with the pseudo wave function and with the all electron wave function coincide for a given, so these two logarithmic derivatives coincide at the eigenvalue where we have fitted the wave function. But what happens just outside this eigenvalue? Well, there is an important relationship, that is this one, that I will not derive because it is not important, the derivation of this, to understand the rest, at least. It is very important that there is this relationship. However, what does this relationship say? It says that the derivative with respect to the energy of our logarithmic derivative is related to the norm up to r of our wave function. So this means that if the pseudo and the all electron wave function satisfy the norm conservation condition, at the point where we made the fit, because the norm conservation condition is satisfied at the energy of the eigenvalue. At this point, also the derivative of the logarithmic derivative with respect to the energy coincide. So it means that at least there is a range of energies in which the logarithmic close to the eigenvalue where we made the construction of the pseudopotential, where the logarithmic derivative, the all electron and pseudo, by construction coincide if the norm conservation condition is satisfied. So it is very important to have this norm conservation condition, because it can give a logarithmic derivative that coincides for a given energy range. So let's see an example of this logarithmic derivative, how they are, what is their shape. Let's take in silicon at the point.
Excuse me?
Yeah.
Can you just go back to the previous?
Yeah.
So that last equation that was just, it doesn't come from any constraints. It was just put together to ensure.
No, this equation is not a constraint. It is an exact relationship between the derivative of the logarithmic derivative the derivative with respect to the energy of the logarithmic derivative and the square modulus of the wave function up to r. This is an exact equation that links this logarithmic derivative with the norm of the wave function, and that tells us that imposing the norm conservation, actually we are imposing the equality of the logarithmic derivative.
The right-hand side is the norm, right?
Huh?
The right-hand side is the norm.
Is known.
Right.
Also, this is known.
So that comes by substituting Fe into that equation. Is that the way?
Yeah, the logarithmic derivative you can calculate once you have your solution, the solution of this equation that gives you the psi at all energies. You can calculate the logarithmic derivative. It's just the derivative with respect to r of a logarithm, and you do it for all energies. So this is a well-defined function, and also this is a well-defined function when you have your solution. And this is an exact equivalence. That tells you that imposing the non-conservation is important because you are imposing that this derivative with respect to the energy of the logarithmic derivative for the whole electron and the pseudo wave function are the same, close to the point where to the energy where we made the construction of the pseudopotential. So, for instance, in silicon, the logarithmic derivative of the S part at 2.1 atomic unit has this form. And this is the energy, this arrow indicates the energy at which we made the construction of the pseudopotential. This is the eigenvalue 3s of the S channel. At this point, in red, in color, in red, we have the all electron logarithmic derivative of the S channel. And in black, it is the logarithmic derivative that you obtain with the pseudo wave function. It is clear that if the non-conservation condition would not be satisfied, then there would be no reason that the all electron and the pseudo logarithmic derivative has the same derivative here. So the black line would go like this. And so the two logarithmic derivative would coincide only at the fitting point. But the fact that also the derivative of this logarithmic derivative coincide tells us that for a certain range, the two must coincide. And the range is quite large. You can see here it is in Rydberg, the energy. It goes from -3 Rydberg to okay, here we have 0.5 Rydberg. There is a complete coincidence. And so it is clear that this pseudopotential reproduces the property of the whole electron in all this range, at least for radii larger than the fitting radius, the core radius. Here we took actually also a radius slightly smaller than the core radius. That then we will see. For the P channel, it is the same thing. For the D channel, you see that there started to be a small difference up here between the whole electron and the pseudo logarithmic derivative.
I have a question.
Yes.
Does the silicon system atom have D states?
No, it has not bonded these states. It has not these states that are bounded to the nucleus, but you can solve the equation, this equation for an arbitrary energy, and this you can do at any energy. Either if there is the bound solution, that means that you have a solution that goes to zero also at infinity. The unbound solution you have at any energy, you have a solution. So if you decide the energy here and put in the TL the L equal to, that corresponds to D, you can solve this equation and calculate the logarithmic derivative. In principle, you can calculate the logarithmic derivative for any L channel, for any L that you want, and for all energies that you want. Okay, so it is clear that this shows that the pseudopotential concept could be quite useful because it allows you to reproduce. So even if you took a configuration of the electrons that changed the energy of the eigenvalue a little bit, still, if you use this pseudopotential in another environment where the energy of the S state is different from this one, but still the pseudopotential reproduces the all electron properties. There is a if that in a while we will see. So this is done, remember, at fixed Kohn-Sham potential. So we fix the charge density and we did this procedure of the logarithmic derivative. In reality, when we change a configuration, we are changing also the charge. So it is another question to see if when you change the charge, the pseudopotential will still reproduce the whole electron behavior. However, let's remind what we have to do to generate a pseudopotential. So to generate a pseudopotential, we have, number one, we have to choose the electronic configuration of the atom. Number two, we have to define the core and valence state. Number three, we have to choose the effective potential and the radius R-lock, after which the effective potential coincides with the whole electron potential. And then for each orbital angular momentum L, we have to choose the function phi L for R larger than the core radius. So the point 1 and 2, okay, depend on the atom, and you can in some sense see what has been already done in the literature and find what usually people take as core and valence, or to decide yourself based on the plot similar to the one that we have seen proceeding. To choose the electronic configuration of the atom, this in principle should not be important. So if you generate the pseudopotential starting from the ground state configuration, as we have used, so in silicon we have used the ground state configuration, or you choose a slightly ionized configuration or an excited configuration, should give pseudopotential if the pseudopotential are transferable enough that are equivalent. In principle, sometimes also this configuration, this is in principle. In practice, sometimes also the electronic configuration could do a different, but it should give a very small difference. Usually, if the electronic configuration is very important, it means that you have core states that should be in the valence. Okay. So let's now discuss these 2 points. How do we choose the effective potential, and how do we choose the pseudo wave function? So the effective potential. In the code, this is something that is discussed in a lot of papers. So this is the choice that we did in LB1.x. It is not guaranteed that it is the best choice. Maybe that you can find something better, or you can implement even something better. However, this is what there is so far. And we have 2 ways basically to define the effective potential. One is to say that the effective potential coincides with the Kohn-Sham potential for R larger than the local radius. And for R smaller than the local radius, we take a sum of 2 Bessel functions of order 0. And these are spherical Bessel functions of order 0. And the parameters are chosen, this A1, Q1, A2, and Q2, in order to have a continuity of the effective and of its 2 radial derivative. The other possibility, so this is a fixed recipe, the only ingredient that you have to give is what is the core radius of the pseudopotential, the local radius of the local potential. This local radius is quite important, and it is a parameter that decides sometimes how good the pseudopotential is, and if the pseudopotential, but we will discuss later. However, this is one input. The form of the potential is defined by this. The second possibility is, okay, I can